This podcast is brought to you by LMU Munich.
Okay, so let me start by quickly summarizing the things that I went over last time, and then we'll resume our discussion of entanglement entropy in two-dimensional quantum field theories. So first, I've given you a very elementary argument that shows that scale invariant field theories in two dimensions are conformal. Then I have given you a derivation of the trace anomaly equation in two dimensions, where T mu is equal to C over 24R, where R is the Ricci scalar. Then we've discussed the fact that we can define a modified energy momentum tensor, which is not covariant, but it's holomorphic. It's non-covariant by some Schwarzian derivative term. The two-sphere partition function, we've argued, is given by an exponent of the logarithm of the radius of the two-sphere, with the coefficient being the central charge. And this is a two-sphere of radius A. Okay, and then we started discussing entanglement entropy in two-dimensional quantum field theory. So we take some slice of space, let's say time equals 0. We divide it into A and the complement of A. We define the density matrix by integrating out everything that's in the complement of A. The Rayleigh entropies are defined in this way by traces over this density matrix. The Hilbert space of A is just the space of all the functions of A, and we can then try to evaluate the density matrix, like an arbitrary matrix element of the density matrix, given by some functions f and g, and that's given by a very formidable path integral that will be very hard to solve. Even in free field theory, it's extremely hard to solve, and I don't think it was done. But in principle, you would have to integrate over all the fields which are continuous in the complement of A. Sorry, this is x in the complement of A. It's continuous, but when x is in A, where this is the region that we want to study in entanglement entropy, then when the time is very small and below 0, then it's f, and very small and above 0, it's g. So it's as if there is a branch cut. So this interpretation shows that so if A consists of a disjoint union of intervals, this path integral computation, yes? No. If no, there is no logarithm. I think that's the conventional definition. So this is time equals 0. So from this path integral representation of the Rayleigh entropy, you see that this region in which you want to evaluate the entanglement entropy or the Rayleigh entropy looks like a branch cut. So when you come below, you're not going to coming below and coming from above leads to very different answers. So the boundary condition for the function here is f, and above it's g. So the idea is that we should really try. So the idea is that one should think about these things as branch cuts, and we should think that we've extended R2 into some covering of flat space. And this is the natural geometric setting where you can compute the Rayleigh entropies. So let me just make a claim, and then I'll explain it by a picture. So the claim is that Sn is equal to the path integral, so over these fields d phi. But now instead of a Rn, this is a path integral over a space which I will call Cn. So the space on which we put our theory now is Cn. So let me put it here, where Cn is a union of n copies of R2, and they're glued in such a way. They're glued exactly on A. So where A is the region for which we want to compute the entanglement entropy. So we get this space which is a union of R2s. And the way the space looks is, so we have a plane, and we have branch cuts. This is where we want to compute. This is the region for which we want to compute the entanglement entropy or the Rayleigh entropy. And the idea is that the path integral representation for the Rayleigh entropy is that you have like n copies of this thing, and they're exactly glued at the branch cuts. So the trace takes care of that very nicely, because the nth copy is glued to the first copy. So it forms a sensible covering of R2, an n-dimensional covering of R2. And if you could compute the path integral over this space, then you would be in business. You could extract from that the Rayleigh entropy. Is that clear? So the claim is that the Rayleigh entropy is just the path integral over some branch covering of the complex plane, an n-dimensional branch covering of the complex plane, where the exact details depend on which region you want to compute for. Okay, so let me just make a few general comments. So this, of course, forms some Riemann surface. So one finds a certain Riemann surface, and the genus is n minus 1, where n is the number of intervals, times little n minus 1, where little n is the Rayleigh entropy that you want to compute, and capital N is the number of intervals. So this is a small exercise that you can do at home. I think it's in the notes. That you can convince yourself that in this way, then you can just compute the number of cycles of non-contractible cycles, essentially. So you can convince yourself that that's the number of non-contractible cycles, and so you get some Riemann surface. So the computation of the Rayleigh entropy is essentially given by some path integral over some Riemann surface of genus G. Over some Riemann surface of genus G. Of course, you know that these Riemann surfaces, they have complex structure moduli, and you have to specify them, and that's a very complicated problem in mathematics. Given some branch cuts with coordinates, given the coordinates of these branch cuts, the lengths of the intervals, the distances between the intervals, there is an in-principle procedure to find the complex structure moduli of the corresponding Riemann surface, and then you can try to compute the path integral. Okay, so this is a path integral over some Riemann surface. So that's how the Rayleigh entropies behave very nicely, but from this point of view, it's not clear why the von Neumann entropy needs to exist, because you need to analytically continue in the genus of the Riemann surface, and it's not clear that this analytic continuation would exist. Let me make one comment in passing that for C equals 1 models, this is not something I'm going to write on the blackboard, but for C equals 1 models, if you take 2 intervals, then it's possible to solve this problem, and it has been solved. People computed all the Rayleigh entropies for 2 intervals for C equals 1 models, and it's not clear how to analytically continue to n going to 1 and extract the von Neumann entropy. So it's not clear whether this analytic continuation needs to exist. And at least in one example where all these computations have been done, C equals 1 models in 2 dimensions, it wasn't clear how to analytically continue for generic values of the moduli. So it's an issue that needs to be understood. Yes?
So could you repeat again how to stick the different R2s together, or how to do them?
Yes, so my artistic skills are extremely limited, but I will try again. So imagine that there is like some parking lot, okay, and there is like one way of climbing to the next level here, and another way here. Okay, so this is our branch cut. Okay, this is the intervals for which you want to compute the entanglement entropy. So you imagine that there are many sheets which are on top of each other. Maybe I'll try to draw a better picture. I'll make some effort, but it's not guaranteed to work. So we have n copies. First, we start with just n copies of the complex plane on top of each other. So they're really just above each other. Okay. And then they all have this 0 time slice. Okay, they all have this 0 time slice. And then on this 0 time slice, you define some disjoint union of intervals or whatever you like, for which you want to compute the Rayleigh entropy. Okay, and they're all the same. Like you just repeated the same for all of them, and then you glue them here.
Okay, so the
Gluing means that if you come from above, there is a ramp. It's like a parking lot. If you drive from this direction, you have to go up, and then you have to go down and so on.
The point where the ramp touches the plane, to me, you don't look as if it would be a Riemann surface at that point.
There is a conical deficit. So if you go around this point, if you start driving around this point, okay, then you'll have to go to the 2nd floor, and then you'll go to the 3rd floor, and then you'll come back. So this is as if there is a conical deficit angle. It's not a deficit, it's a surplus, a conical surplus. It's really. So you're saying that this point is not a regular point?
Yes,
Oh.
So yeah, it's looking like if it just stick on a ramp, that where the ramp touches the bottom.
Yeah, this is not a regular point, but you should think about it as a deficit angle singularity. This follows from the Gauss-Bonnet theorem. You know that the integral over the Riemann curvature over some Riemann surface S has to be given by something like 6g minus 6. If maybe I'm getting it wrong, g minus 2 or something. So if the genus is large enough, you need some deficit angles. You need to have some curvature somewhere in order to satisfy the Gauss-Bonnet theorem. So here it's realized by some deficit angle, but you can smooth it out. In the end, you can just describe it by some completely regular Riemann surface. Okay, so there is one example in which this has actually been done, which is the case of two intervals c equals 1. This was done by Cardi and Calabrese for the Luttinger liquid theory, which is a compact boson. And it's not clear how analytically continue. Nevertheless, I think it's believed that the analytic continuation should exist. We don't have a path integral representation for the limit of n going to 1, but I think it's believed that it should exist. Or at least the observable should make sense. Okay, so now I'll discuss the case of one interval. One interval is obviously very special, because you see from the formula for the genus that the genus is 0 if you have just one interval. That means that you can solve the uniformization. You just need to solve a uniformization problem, meaning that you have to map one interval to the plane. It can be mapped to the regular plane, because the genus is 0. And in the end, the Rayleigh entropy calculation just boils down to some computation in flat space. So that's what I want to show. How to solve the problem of one interval, which is the simplest possible problem in this class of problems. Okay, so one interval. Are there any more questions about the general setting? Okay, I should also mention that perhaps you would think that this problem should be solvable for minimal models, at least, but it wasn't yet done. So we don't know the Rayleigh entropies even for minimal models. So let's discuss one interval. So the case of one interval is obviously very special because the genus is 0. So one interval means that we have this thing, then there is a branch cut which extends from A to B. And then we glue, so suppose we want to compute Sn. So Sn would mean that we take n copies of this thing and glue them in the way that I've just described. But the genus is 0 because the cycle that goes around A and B can be expanded and contracted through infinity. So there are no cycles, the space is topologically just a sphere. So how do we solve this problem? One needs to uniformize it, to map it to the sphere in some convenient way. So we have to map this space to a sphere in some convenient way. So I'll just describe how to do that in pictures, and you will fill the details yourself. Okay, so the first step is that you recall that there is a conformal map that takes an interval to a semi-infinite line. That's a standard result in complex analysis, that we can map any interval to a semi-infinite line, to, let's say, the line that goes from 0 to infinity. So first we can make the branch cut go all the way from infinity to 0, and that's just a holomorphic map, a holomorphic coordinate transformation. So you can, without loss of generality, think about the interval as if it extends from 0 to infinity. And that's so this is like computing the entanglement entropy over a half space, a topic which I understand Juan covered in detail. So at this point, it's already isomorphic to what Juan explained. The density matrix, the density matrix in this case would be the boost matrix, and one can compute the von Neumann entropies just from that. But I would like to compute all the Rayleigh entropies. So I'll explain in a bit. I would like to explain how to compute all the Rayleigh entropies in this case. get some simple analytic form. So this is the first step. So now our space can be actually drawn quite simply. We have this plane, and we have this branch cut that goes to infinity. And well, and every time you cross the branch cut, you go to the next level of the parking lot, and you keep circling until you go back after you do that n times. So that's really a simple parking lot. There is just one stairs that takes you always upwards, and then in the end you go back to the first floor. So that's really easy to imagine. This can be uniformized. So this can be mapped to the sphere by the following map. Omega is equal to z to the power 1 over n. So if the coordinate on this parking lot, which has n floors, is z, then the coordinate omega would be just a coordinate on a flat space. So this is already a coordinate on C. Okay, so you see that there is this sequence of maps that takes any interval to a flat space. And now, one additional thing that you need to recall is that the energy momentum tensor is non-covariant. It's holomorphic but non-covariant because of the trace anomaly, which is what I explained in detail last time. So we need to compute the Schwarzian derivative for this thing. So you need to compute the Schwarzian bracket for z to the power 1 over n z. This is the energy momentum tensor would shift by that. So t prime would be t plus this with some central charge here, with some coefficient. So you just need to compute this thing. It's very easy, of course. And from that, you find something like the energy momentum tensor on the plane is now not 0, as it usually. Sorry, so let me just write the precise formula. So this Schwarzian derivative means that the energy momentum tensor is non-zero. Even if it's 0 in one frame, it would not be 0 in the second frame. And what you find is you can interpret this non-zero result as saying that this insertion here has a non-trivial anomalous dimension. And you can just compute this anomalous dimension in a way that I will explain momentarily. So we got C over 24, 1 minus 1 over n squared, where n is the Rayleigh entropy. So basically the statement in the end boils down to this magic formula. If you have an interval, for say many intervals, this is always true. If you have any of these intervals, then computing the nth Rayleigh entropy means that you need to introduce some conical deficit here that would make you go n times around until you come back. So introducing this conical deficit can be thought of as if you are introducing some local operator with this dimension. And this dimension follows just from this Schwarzian derivative, because the Schwarzian derivative tells you that the energy momentum tensor in the vicinity of this singularity is non-zero, it's singular. So how do we read out dimensions in conformal field theory? The dimensions are the coefficients of some singularity that multiplies the operator whose dimension we would like to read out. So if you have an operator of dimension delta and you try to measure the response of the energy momentum tensor when you're placing the energy momentum tensor near the operator, there is a second order pole whose residue is delta. This Schwarzian derivative is singular because it involves a function which is non-analytic, and this would lead to some second order pole. And the residue of the second order pole we just interpret as a dimension of an operator that sits at the edge of this interval. Okay, so this is the dimension that one obtains. And from that, from that you see why just one interval is special. One interval is like a 2-point function for these local operators. Well, when you have more than one interval, it becomes very complicated. You need to understand higher point functions. But the Rayleigh entropy is just given by a 2-point function because there are just 2 points which are singular. And in this picture, well, it's 1 point and the point is infinity. So, and 2-point functions are fixed by conformal invariance. So, the entanglement, the Rayleigh entropy is just given by a 2-point function for these two conical deficit singularities. And because there are n copies of the plane, you need to multiply by n. So in the end, what one finds is that the Rayleigh entropy is 1 over n minus 1. And then there is a minus b. I'm uniformizing back. So I'm going back through these coordinate changes to the language where there is a and b. And you just compute the 2-point function of these operators that are separated by a minus b. So one finds a minus b to the power c over 6 n minus 1 over n. So usually the power that you would encounter in computing 2-point functions is just the dimension. So it would be 1 minus 1 over n squared. But here there are n copies of the plane. So you need to multiply this by n. Because you're computing the 2-point function, then you need to remember that you're really interested in the partition function on the n's covering. So there is one additional factor of n. So this is the final answer. We don't know the prefactor, but we know the exponent. So there is some prefactor here that may not even be universal, but we don't know it. We just know the exponent. So we know the dependence on n. The exponent dependence on n. And this has a very natural analytic continuation to n going to 1. I mean, it's just a nice function of n, and you can just analytically continue it. And one can read out from this the von Neumann entropy, which is given by the logarithmic derivative of this thing. And that's just c log a minus b. And that's the central formula. So you see that the von Neumann entropy for an interval is just, again, given by the ubiquitous central charge. So it's completely fixed by the central charge. It doesn't depend much on the details of the model. Okay. Now, if you look at computations for more than one interval, let's say 2 intervals, then it starts depending on the parameters of the theory in a much more sensitive way. So for example, in C equals 1, you have a parameter, an exactly marginal parameter, which is the radius of the compact boson. And the formula for 2 intervals depends very, very crucially on the radius of the compact boson. Okay. But if you just have one interval, then it's just a central charge. It doesn't know about the radius and so on. So are there any questions about the steps in this computation?
So if you had a central charge just smaller than 1.
Smaller than 1, yes.
So it's a minimal mode. Then is it clear that these operators are there?
No, these are not operators in the theory. These are operators that are like external defects that create conical singularities. But since you asked, I'll answer. So for those of you who know CFT, a little bit two-dimensional CFT, I'll answer this question in a little bit more detail. So this is just for the more advanced students. So if you have such a conical singularity and you just measure the energy momentum tensor near it, you would find that it has a second order pole, just because it's a singular geometry. And you can associate that to a dimension of some fictitious operator that creates this conical singularity. But it's not part of the theory. It's not an operator in the theory. It's not part of the spectrum if you look, of the normal theory. But you can make it part of the theory in the following way. So you can rephrase everything that I've said in the following way. You can say that computing the Rayleigh entropy is the same as taking the n's symmetric product of the CFT with itself. So you do CFT, tensor CFT, tensor CFT, n times. And you divide by the thing so that it would be a symmetric product. And then these are just the twist operators that connect all the n copies of the CFT. So essentially the Rayleigh entropies can be understood if you just want like a completely axiomatic definition of what we're talking about. So Sn is just the endpoint function of some twist operators in the symmetric product CFT. And you can check that, with usual tools of CFT is that the dimensions of the twist operators in these theories are precisely those. And so then you can try to compute these endpoint functions in the symmetric orbifold. Okay, so then, this is a pure CFT problem. And this computation is like in flat space. We don't need this trick with the covering anymore. Okay. So that's one way to make it a little bit more abstract. Okay, now I want to make some final remarks about 2 dimensions before we go into 3 dimensions. by the way, I just wanted to mention that there are many very concrete and simple open problems. I mean, they sound simple. I don't know if they're simple in practice, but for example, you would like to understand the large n asymptotics of the Rayleigh entropies. That is more or less, so that would be sensitive to the largest eigenvalue of the density matrix. So you could try to understand. Such elementary questions don't have simple answers yet, as far as I know. The large n limit and so on. Little n, I mean, large little n. Okay. So just one more topic in 2 dimensions that I wanted to cover is what happens. So far everything was just about CFTs in 2 dimensions, and now I want to discuss what the Zohar-Komargodski C-theorem, which tells you that there is some interesting structure when you start deforming these theories. Okay, so everything so far was just about CFTs, all these formulas and all these nice results. But suppose we had a 2-dimensional CFT which was deformed so that the correlation length is no longer infinite. It was deformed by something, and you get a new CFT in the infrared. And the question is, what can you say in general about it? So in the 80s, Zohar-Komargodski proved that the central charge that we discussed and that appears in many, many places. It appears in the entanglement entropy. It appears in the sphere partition function. It appears in many other observables in 2 dimensions. And Zohar-Komargodski proved that C of V is bigger than C infrared. Okay, so given that this is the central charge appears in the entanglement entropy, you can try to understand that as some consequence of information theory. So it's just some consequence of the way entanglement entropy behaves in general. And it's closely related to the subadditivity inequality that Juan mentioned in the previous lecture. But the conventional proof of this had nothing to do with entanglement entropy. It was later reinterpreted as a result about entanglement entropy. So there are several ways to prove this thing. I'll just sketch the original derivation. You can read about more recent derivations elsewhere, and the references are in the notes. So the conventional derivation goes more or less as follows. So we've classified, I'll just sketch it. I'm not going to do the details. The details are in the notes, and they're not particularly illuminating. This inequality by itself is very illuminating, and it's very important, but the details of the derivation are not particularly illuminating. So one studies this 2-point function of the energy momentum tensor that we discussed at great length previously. And the difference from conformal filters or scale invariant filters is now that these functions f of q squared and g of q squared that I defined in the previous session are no longer just a over q squared or b over q squared. They are non-trivial functions. So now there are non-trivial functions which depend on the mass scale of this relevant deformation. So this relevant deformation has a mass scale m, and it depends on the mass scale. So these are now non-trivial functions. And the idea of the proof is that if you look at this object, so t mu x, t nu 0, so this is some 2-point function. And by reflection positivity, or if you want this Riesch-Liddell theorem, this has to be bigger or equal to 0 on the one hand. But on the other hand, you can write some differential equation which looks as follows. So let's call this function very roughly h. You can define this function as h. It's some combination of f and g in this language. So you can define a certain quantity c such that c dot is 6h. And since this is bigger or equal to 0, so maybe we'll put here a minus sign. Sorry, no, I want to put a plus sign. So c dot is 6. You can define a certain combination c, which is in the notes, such that its derivative is 6h. Okay, so this combination is not very illuminating, but it can be defined. And since this is bigger or equal to 0, you find a certain function which is monotonically increasing as a function of the RG scale. So if this is growing energy, then this function C monotonically increases with a derivative that is fixed by some positive definite two-point function. And then there is one more step, which is to show that at very small mu, this goes to C infrared, and at very large mu, this goes to C UV. And that shows the inequality. This also leads to a very interesting sum rule, that this is what I wanted to emphasize, that C UV minus C infrared can be written as an integral over all of space of T mu mu x, T nu nu 0, with an additional insertion of x squared. I'll just get the coefficient straight, and I will write it. So there is just an x squared here. Okay, so this is the central result. So we'll see another derivation of that in the future, so I don't want to spend too much time on the derivation now, but the idea is that you study again this two-point function from which we already extracted some mileage, and you can find some function C, which is monotonically increasing, then you can integrate it, and you find this interesting sum rule, which is, of course, manifestly positive. Yes?
This is in Minkowski space, yeah?
No, this is in Euclidean space.
Is there a C-theorem in curved space-time?
A C-theorem in what? In curved space?
Curved space-time, or
What would you mean by that?
Lorentzian two-manifold.
Lorentzian two-manifold. But there is like one C. It's not that there is like different C's. There is one C. So this is just a statement about any renormalization group flow has some C here and some C here. You can put it on a curved manifold, but it's still the same RG flow. Okay, so this is just a sketch of a node result that you can read about in the notes or in the original papers. Okay, so there is a big collection of results in 2 dimensions that I outlined, and now I want to discuss 3-dimensional models, which present many new difficulties, and also their analysis is much more recent and still ongoing. Okay, are there any questions about 2 dimensions? Any additional questions about 2 dimensions? Okay, so I'm switching to 3-dimensional models. Okay, so 3 dimensions. So let me just outline what I'm going to discuss in the context of 3-dimensional field theories. Unfortunately, it's riddled with some subtleties that we would need to cover to understand exactly what the various claims mean. So we'll have to cover. So we'll have to start our discussion from QED in 3 dimensions. This theory is a little bit more subtle than it appears, but understanding these subtleties would be crucial to understand some results about entanglement entropy and the sphere partition functions. So we'll try to cover some subtle issues that concern with QED in 3 dimensions, and then we'll discuss 3 sphere partition functions and entanglement entropy. I could also discuss a little bit of supersymmetry in 3 dimensions, depending on how much time I've got. This is not something that I'm sure that I'll be able to get to, but these are very important. So when you compute entanglement entropies in 3 dimensions or sphere partition functions, there is a certain subtlety that one encounters that I would like to explain. So for that, we need to analyze a free field theory, which is the free Maxwell theory. free Maxwell theory in 2 dimensions. Okay, so this theory presents a few subtleties that are very important to understand. So first of all, this is manifestly a unitary theory. It can be quantized, and it was quantized, I think, many years ago. It doesn't have any ghosts or any negative probabilities. It's justifying quantum field theory. But in regard to the question of whether it's conformally invariant or not, there are some subtleties, and they affect very importantly the question of how the entanglement entropy behaves as a function of the radius of some surfaces. So we need to understand that. So let's start by writing down the energy momentum tensor. So we need to write down an energy momentum tensor that satisfies a few properties. It has to be gauge invariant. That's one property. The second property is that it has to be symmetric in the indices, and it has to be conserved. Okay, so and it has to have dimensions 3. So we need to write down some energy momentum tensor of this sort, and there is only one energy momentum tensor you can write, which is this. Okay, so this is the energy momentum tensor of the theory, ff minus a quarter at mu nu f squared. You can check that it's immediate that it's gauge invariant, it's immediately clear that it's symmetric, and you can also check that it's conserved. The problem with this energy momentum tensor is that it's not consistent with conformal invariance. So in what sense? So even though this theory doesn't have any mass scale, it turns out that it's not conformal. So you could think that you would assign the gauge field dimension 1/2. You would assign a derivative at dimension 1. And then the electric charge would be would be dimensionless. And this would appear to be a scale invariant unitary theory. And then you would think that it's conformal. But there is some obstruction here. This obstruction is very central to understand some results about entanglement entropy and sphere partition functions. So in general, if you want a theory, if you have a scale invariant theory, then you expect to have a scale current. So this is a current whose charge is basically the scale charge. And the current needs to have the following general form. And V mu is called the virial current. So any scale current needs to be of the following form. It needs to be x times t minus v mu. And the interpretation is pretty clear. I mean, t mu generates translations. Once you multiply it by x, it generates rescalings. And then you may need to subtract some vector that would somehow be interpreted as a change of variables of the fields or changes of coupling constants and so on. And this is called the virial current. So this is the most general form of scale current. But this is conserved. So this scale current is conserved if and only if the trace of the energy momentum tensor is given by d rho of the virial current rho. Okay? So this scale current is conserved if and only if the energy momentum tensor is a divergence of something. This energy momentum tensor is not a divergence of anything. So in QED in 3 dimensions, the trace of the energy momentum tensor is f squared. Okay, with some coefficient. So let's get the coefficient squared correctly. It's a quarter. Okay, so the trace of the energy momentum tensor is a quarter of f squared. And I challenge you to write that as a divergence of something that is gauge invariant. It's impossible. It can be formally written as a divergence of something. So it would be a half d rho of f rho nu, a nu, where a nu is the gauge field. But that is not gauge invariant. So we find that there is a clash. So there is a clash between gauge invariance and the existence of a scale current. So you have to choose either you preserve gauge invariance or a scale current. or you have a scale current. So this is strange. This is a theory which on face value looks like scale invariant, but in fact it doesn't have a scale current. So it would seem like a violation of the Netter theorem that they would say that every continuous symmetry is associated to conserved current. In this case, there is no conserved current because it's not gauge invariant, so it doesn't exist as part of the theory. Okay, so this is a very... Are there any questions about this elementary statement? Yes? Yeah, of course I'm going to get to that. So there is no scale current. However, let us try to investigate. Let us suppose that you insisted on taking this scale charge to be non-gauge invariant. So we will have a scale current which is non-gauge invariant. It would be given by x nu p mu nu. Let's pick this v. Okay, let us use this v seriously. So it would not be gauge invariant, but we would use it anyway. So we would add a half f rho nu a nu. So this is a scale current in this theory. It's conserved, symmetric, but not gauge invariant. But this is not a big deal, because it turns out that the charge associated to this is gauge invariant. So the charge is gauge invariant, even though the current is not gauge invariant. And to see that, you just notice that the gauge variation of the charge, so this is the variation under A goes to A plus d mu alpha. So the gauge variation of this thing is proportional to the integral of di f0I alpha, which vanishes by the equations of motion. And here I've done integration by parts. Okay, so this is a very peculiar theory which has a scale charge. It doesn't have a scale current. And for the conformal charges, meaning the special conformal transformations, the situation is even worse. There is neither a current nor a charge. So to summarize, I'll just make a small table. So there is the scale current, a scale charge, and then there are the conformal currents and the conformal charges. So QED3 has that. It doesn't have a scale current, it doesn't have conformal currents, it doesn't have conformal charges. Okay, so this is the situation with this theory. Okay. Okay. Are there any questions about this? Okay, now there is a very useful way to think about this theory, which this is somehow simplistic. There is a more precise way to think about this theory, which has been recently tested by some entanglement entropy computations, and I think it's the correct way to think about this theory. So this is what appears in some papers and maybe even in some books, but there is a more correct way to think about this theory, which I would like to explain. Incidentally, as you remember, in 2 dimensions, we've shown that scale invariance implies conformal invariance, of course, with unitarity. The existence of this theory immediately shows that such a simple statement cannot be made in 3 dimensions, because there is a counterexample. But this is a free counterexample, and it may look like a fluke in some sense. So most people believe that a statement would exist eventually, which somehow would take this theory into account. But there is no such statement yet. So you see that the question of scale invariance versus conformal invariance in 3 dimensions is much more involved than in 2 dimensions. Just from this simple counterexample, you see that this is going to be troublesome. So there is another interpretation of this theory that is extremely useful, which involves Poincare duality. So in 3 dimensions, it turns out that the scalar theory is completely identical to a gauge theory, to a gauge field, to an abelian gauge field. Okay. So this is a result that is true in 3 dimensions, and it's realized by the following formula. You can take the field strength, use the epsilon tensor, and get the derivative of the scalar. This scalar is a free field theory scalar because the Bianchi identity of this guy, so the Bianchi identity of the field strength is translated to the Klein-Gordon equation of phi. Okay, so a free scalar field theory is dual to an abelian gauge field theory, and using the scalar, one can arrive at a somewhat better interpretation of the results quoted above. So this is somewhat. So this identification needs to be clarified a little bit. What exactly does it mean? So so one has to distinguish gauge fields with an abelian gauge symmetry that is compact from gauge fields whose gauge symmetry is non-compact. So let me explain what I mean by that. So an ordinary gauge transformation looks like that. Well, I used the letter alpha before. This is an ordinary gauge transformation. But one has to be careful in understanding whether this alpha is part of a circle, lives on a circle, or it's just part of the real line. So this is the question of whether the gauge symmetry is U1 or it's really non-compact, so it's R. So if alpha is identified with alpha plus 2 pi, you would say that this is U1, and if alpha is just an element of the real line, this would be non-compact. And this duality this duality has different interpretations in these two cases. So this is a compact. This is an example of compact. And if alpha is in R, and without any identifications, this is non-compact. So if you have a compact gauge field, then this scalar is periodic, because so if you have a U1 gauge field, so by this I really mean that the gauge symmetry is part of a circle, then this is dual to a compact scalar. If you have an R gauge theory, then this is dual to a scalar whose radius is 0. So this is a scalar without a zero mode. A scalar for which phi is identified with phi plus c for every c. So this is like a scalar whose radius is 0. It's a scalar without a zero mode. Okay? So this is another. How do you see that? So from this equation, it's quite obvious. You imagine that the theory is defined on some 3 manifold, which has some cycles. Then if you integrate the right-hand side on some 2 cycle, there may be some magnetic flux. And then you need to reproduce the same answer from the dual cycle on the left-hand side. This is why it's called Poincaré duality. This is exactly the duality between forms that is named after Poincaré. So the integral on the left-hand side would be non-zero only if I can wind around if I can wind around the circle. Or if the integrals of f vanish, that means that the gauge field is non-compact, and so phi doesn't need to wind around anything. So that's how you can see that these are true. Okay. So now, yes. Okay, so the question is whether this can be done for non-abelian gauge theories. This is a great question. I think that some people would say yes, and some people would say no. It depends exactly on what you mean. So what people most often do, this is for example what Polyakov did in his seminal paper, is that you take a non-abelian gauge theory and you go to some Higgs phase where the actual gauge symmetry is just U1, and then you dualize the U1 to that. So this is not a full-fledged non-abelian duality, that's just dualizing some U1. And that's what Polyakov did in the seminal paper on confinement. There are some versions of that. Some papers contain more elaborate versions of this idea that would seem to hold even in non-abelian cases, but I don't know if they're useful or even correct. But no,
The quantical
conventional, yes,
it's still a billion.
exactly. The conventional results that I think everybody agrees on always end up being just some variation of that. You can't uplift the duality that Polyakov used to the full SU2 gauge theory. We don't know how to do that. Okay. Okay. So now one can so this obstruction that we found concerning scale and conformal invariance can be very vividly understood in terms of the scalar language. The reason is the following. So if you try to write down an energy momentum tensor for the scalar, so you need to write down something that is conserved and symmetric, and essentially there is only one thing you can write. So let me write it down. So this is an energy momentum tensor that is conserved and symmetric, and it's not traceless. So the theory is again non-conformal. But if you just deal with ordinary scalar fields in 3 dimensions, of course they can be rendered conformal. So what one finds that is one can add an additional term. So let me just write it down and then I'll explain what it means. Okay, so forget for a moment about everything I've said. If you ask yourself whether the scalar in 3-dimensional field theory is just an ordinary scalar, has a traceless, conserved, symmetric energy momentum tensor, the answer is, of course, yes. And this is it. You can check that this energy momentum tensor is conserved, symmetric, and traceless. However, now you see what's the problem. The problem is that this term that we add, the last piece here, is not invariant under shifts of phi. So it's not consistent with the compactness of phi. So in terms of the scalar field, it's more or less clear why the theory fails to be conformally invariant, even though it's scale invariant. It's because this piece is not consistent with the periodicity of the scalar field. Okay, so this is a reinterpretation in terms of the scalar of the problem that we found for the gauge field. But this is just a technicality. There is a much more profound implication of this Poincare duality that I think allows for a much more clear interpretation of what's going on. So the scalar field in 3 dimensions, it naturally has dimension 1/2. Okay, that's the conformal scalar's dimension. And so if it's periodic, the natural periodicity parameter would also have some dimension 1/2. So f is something of dimension 1, and we put it in the square root. That's the natural dimension that you would assign in 3 dimensions. But if you are at very high energies, this is a mass parameter. So mass parameters go to 0 at high energies. So at high energies, we find a scalar whose radius is effectively 0. And that's exactly it. So we have an R-gauge theory. In the infrared, mass parameters go to infinity. So in the infrared, you find a decompactified scalar. So really, three-dimensional QED should be described in the following way. We have a 0 radius scalar here. And then we have a relevant perturbation that makes it a little bit, that gives it a slight zero mode. And then this flows via an ordinary normalization group flow to an ordinary Peskin-Schroeder, if you want, non-compact scalar. This is what you're usually used to seeing. So really, 3-dimensional QED is an RG flow from a theory that is scale invariant but non-conformal to a theory that is perfectly scale invariant and conformal. Because by the time the scalar is non-compact, these periodicity conditions do not matter at all. And this is an allowed term to add to the energy momentum tensor. So the theory in the infrared is conformal. So this is a conformal theory. But the theory in the UV is only scale invariant. So this is the correct way to think about 3D QED. As an RG flow from a scale invariant theory to a conformal theory. So this is an R gauge field, then the gauge field becomes compact and it flows to a non-compact scalar in the end. And there are really nice recent computations of the entanglement entropy that show that in the infrared you get exactly the entanglement entropy of a free scalar, which is some finite number. And in the UV, you get something sick that I will explain, because it's not a conformal theory. But just kidding. So this is this is the correct interpretation of free three-dimensional QED. And with all of this, now I can discuss three-sphere partition functions and entanglement entropy. Are there any questions about this? Yes?
So in terms of the gauge fields, you probably would not be able to write such.
Well,
Are you saying that scalar is the correct one variable?
you could have complained in the same way to Polyakov.
I'm not complaining, I'm asking.
Yeah, I mean, you can do the computation of the entanglement entropy that I will describe using the gauge field language, and it gives exactly this result. So it's not that one description is correct. And okay, so no. So I just have to explain that. So the scalar is compact. So the shift of phi by phi plus 2 pi is a gauge symmetry that we don't violate. But the continuous shift of phi by phi going to plus constant with any constant is a global symmetry. And this global symmetry can be broken by relevant operators like phi squared and so on. But in this description, I insisted on preserving this global symmetry. So if you want, that's like taking Polyakov's computation and sending the mass of the monopole to infinity. In this theory, the mass of the monopole is not determined. So you could send it to infinity and ignore you could insist on preserving the U1 topological symmetry. So that's what I'm describing here. I'm describing the pure U1 model where you just insist on preserving the topological symmetry, which is the shift of the scalar. So there are no operators like phi squared that are induced. Those would, of course, lead to a gapped phase.
I'm not talking about adding them to the Lagrangian, but using them to improve the stress tensor. So instead of putting the phi squared term that you have there, you put cosine of phi minus 1 in that position, in that place. It still conserves the stress tensor to obey the shifting.
But it would not be traceless. This is meant to exactly cancel the trace of these pieces. You see what I mean? Yeah. But in the infrared, the theory is conformal. Yeah, but you can't make it traceless all the way. That's what I'm. Okay. Yeah. So we're in agreement. Okay. So this is some free field theory that turns out to be more subtle than one bargained for. And now I would like to describe some recent developments on the three-dimensional field theories that, in order to understand them, one needs to keep this in mind. Okay, so these are S3 partition functions. I think I just wanted to maybe clarify what Juan said. So what Juan said is that you could have started from an energy momentum tensor in the UV, which has a cosine, and then flow to this conformal energy tensor in the infrared, right? So you don't have to add somehow retrospectively add it. You can add something to the UV in the UV that would flow to that. So yes, this is correct. This is of course correct, and it doesn't contradict anything in this picture. Okay, so S3 partition functions. These partition functions have played a very major role in the literature in high energy physics over the last couple of years for several reasons. One reason is that they can be computed exactly in supersymmetric field theories. This is a subject on its own, and I won't have much to say about it because I don't have time. The other reason is that these S3 partition functions naturally led to a generalization of Zamolodchikov's C-theorem. So this inequality is CUV bigger than C infrared, which in 2 dimensions is of course very important, and its importance cannot be overemphasized. It appears that the correct generalization is via S3 partition functions. This is why when we discuss 2 dimensions, I emphasized the S2 partition function. The S2 partition function contains C, so a natural guess of which quantity could be monotonically decreasing in 3 dimensions would be the S3 partition function. But the S3 partition function is very different from the S2 partition function in the following way. So if you take the log of the S3 partition function, it would be in general a divergent quantity. So in general there is a cubic divergence. So let's take the radius of the S3 to be A. And then there will be some linear divergence, and then there will be some constant. In 2 dimensions there was a logarithm. There was a logarithm of the radius of the sphere, as you remember. It was intimately connected to the fact that there is a trace anomaly. But in 3 dimensions there are no trace anomalies, and there are no logarithms. There is a finite piece, a linear piece, and a cubic piece. So A cubed. Okay? Now the hero of the story is this guy, the finite piece. But you have to make sure that it's even well defined. I mean, since there is a linear divergence and there is a cubic divergence, how can you isolate the finite piece in practice? If somebody decided to shift the cutoff by 1, then your finite piece would be contaminated. So suppose your cutoff is shifted by 1 over the radius of the sphere. Okay, why not? That would contaminate the finite part. So I have to convince you that this is somehow not allowed. And there is some universal meaning to this finite piece, even though there are divergences which are linear and cubic in front of it. Okay, so it's non-trivial to establish that the S3 partition function contains any non-trivial information whatsoever. Because if you just shifted the cutoff, this kind of shift of the cutoff is completely innocuous. It would seem to be completely innocuous. You take some big cutoff, which is M Planck, and you shift it by 1 GeV. So your new cutoff is M Planck is like 10 to the 19 GeV plus 1. So what's wrong with that? And then it shifts F by 1 unit. So I have to do some work to convince you that this S3 partition functions contain some information, and that F has a unique physical meaning. It's even measurable in principle in the laboratory. So, and this quantity will be the hero of some recent developments, whereby people argue that this is true for any 3-dimensional renormalization group flow, from some CFT in the UV to some CFT in the infrared. Okay, and this is very closely related to entanglement entropies, and of course it's very interesting to ask what happens to QED3. So the reason that I introduced QED3 was that its F is very subtle, and we need to discuss the F of free QED, and there are many other things that are very interesting and connected to that, which I will discuss. But this is the basic picture, that you need to identify some quantity which exists, then there is some inequality, and you just need to understand how to use it in some subtle examples that contain free gauge fields. Free gauge fields are of course very interesting because many condensed matter systems for which you would like to apply this kind of inequality contain in the ultraviolet free gauge fields, like QED in 3 dimensions plus fermions. That's a very important example in condensed matter physics. So you would need to understand how to use this kind of results. So this is the big picture. Are there any questions? Okay, so let us try to convince ourselves that there is any meaning to this F whatsoever, and that somehow these shifts of the cutoff are not allowed. So we need to classify counterterms. The cubic divergence has to do with the cosmological constant counterterm. So if you add to your generating functional, to the action, just a cosmological constant term, suppose you add the cosmological constant term to your action, that would shift that would shift the cubic divergence of the partition function in some additive way. So in particular, we can tune that to remove the cubic divergence. Now we have another counterterm, which is the Einstein-Hilbert counterterm in 3 dimensions. That would shift the linear divergence by some unit, additive unit. But there are no other counterterms. Just for advanced students, I'll mention that there is one more counterterm that you could imagine, which is the gravitational Chern-Simons term. But this one has an I, because it's a Chern-Simons term. So it doesn't affect the real part of the partition function. It may affect the imaginary part, but not the real part. So you can ignore about the gravitational Chern-Simons term if you don't like it. Okay? So this basically shows that there are just two counter terms, and there are three observable, and there are three quantities in the partition function. There is this, that, and that. So f cannot be shifted away by anything. So how does this resolve the paradox? Why is this transformation not allowed? Why am I not allowed to do lambda going to lambda plus 1 over a? So the physical explanation of why this is not an allowed shift of the cutoff is that when you think about counter terms and the ambiguities of quantum field theory, all the coupling constants need to be promoted to fields. And a is the radius of the sphere. So it's really part of the metric. So to make this thing consistent, you have to find a local counter term in terms of the curvature and the metric, which is diff invariant. So this is why here I'm using local counter terms in terms of the metric and curvature that are completely diff invariant and fine. So the explanation of why this is not allowed is that a here is really the component of the metric, a component of the metric. And this kind of shifts are not consistent with diff invariance. So the short answer to the question of why these shifts are not allowed is that they are not consistent with diff invariance. So you can imagine taking some lattice, and you would be careful about tuning all the counter terms such that you recover diff invariant answers in the end of the day. So my claim is that if you have done that, so you've been careful about preserving diff invariance, then f would be completely unambiguous, because there is no counter term that shifts f. So I claim that every two students who compute f with a diff invariant regulator will necessarily get the same answer. So this is universal. So there are many diff invariant regulators, and the non-trivial claim is that all of them give the same f. Okay. So this is the essence of the claim. This shift is not allowed because a is really a parameter in the metric, and you cannot lift it to something diff invariant. Okay, this is the intuitive picture. So f is universal, and it's a highly non-trivial claim that the FUV is bigger than f infrared in every renormalization group flow. I'll show you some examples now. So let me just sketch briefly how you could compute f in one example. I'll just do the scalar field, and you'll see that the f that you associated to some given field theory is not like an intuitive measure of the number of degrees of freedom. It's some very complicated zeta function, or it's some complicated number that is given by some zeta functions and so on. So let's try to compute f of a free scalar field. This is a conformal field theory, so it's not subtle like QED3. And what we need to do is just to take the log minus log of some path integral over the free sphere. So we do a path integral over all the fields phi, with the action being just the action of a free field on the free sphere, conformally coupled. So there will be some half, and the action would be d phi squared. And then there is a curvature coupling, which is 1 over 8 r phi squared. And r is the Ricci scalar. Okay, so you need to compute this path integral. And that would give you f for a free scalar field. So this coupling to curvature is there just to maintain conformal invariance. Okay, so how do you compute such a path integral? Well, you just need to diagonalize the Laplacian. You just need to diagonalize the Laplacian on the sphere. The Laplacian on the sphere, and it has, of course, well-known eigenvalues, well-known eigenfunctions, and in the end, you just find some infinite sum, which you can, which is written in the notes. So one finds that f is given by the following infinite sum, a half sum over some multiplicities. So this is some multiplicity factor that you can find the explicit expression of in the notes. And then there is n plus 3/2 minus plus log of n minus 1/2. So one finds an expression of this sort, where mn is just a multiplicity factor. So it's n plus 1 squared. So this is some infinite sum that you can evaluate using zeta function regularization. Some straightforward exercise, and one finds 0.063, something of this sort. So the scalar field in 3 dimensions is assigned to have 0.06 degrees of freedom, some infinite number like that, some zeta function. And that's the answer that you need to insert when you come to test this inequality. Suppose you have some free scalar field in infrared, and you can constrain the UV, or vice versa, by this. So this is the value that you assign to a free scalar field, and one can compute the same thing for fermions, and there is some other zeta function that appears for fermions. And this is all quite standard and not extremely interesting. One extremely interesting thing is that there is a huge conceptual difference from 2 dimensions. That's what I want to discuss now in the counting of degrees of freedom. Okay, so now there is a conceptual philosophical point that is extremely interesting, and in 3 dimensions it looks very different from 2 or 4 dimensions. So the conceptual point is that the content of these inequalities is basically like saying that the number of degrees of freedom decreases, okay? But in 3 dimensions, it appears that when you count degrees of freedom, you also need to include non-propagating degrees of freedom, or what you would call topological degrees of freedom. So in 2 dimensions, we saw that the central charge appears in the correlation function of 2 energy momentum tensors. So that is a local probe of the theory, where you excite the energy momentum tensor at one point and measure it at another point. It does not know about topological degrees of freedom, or some non-propagating degrees of freedom. In 3 dimensions, for example, if you take a topological field theory, A wedge dA, where A is a gauge field in 3 dimensions with some level k, and you put some 4 pi for conventional reasons, you compute the S3 partition function. That has been done in the 70s for this topological field theory. It has no propagating degrees of freedom because the equation of motion for A sets the field strengths to 0. And that means that A is a flat connection. It's a first order equation of motion. And the number of flat connections is classified by topological properties of the underlying manifold. And this is topological data. So mathematicians classify flat connections by the number of conjugacy classes of some maps from S1 to M. And this is completely topological data. There is no dynamics in this theory. Yet, the 3-0 partition function was computed in the 70s. In this case, it's given by minus a half log k. So it would seem that f is a half log k. So this is an extremely interesting philosophical point, which is that when you count degrees of freedom, you also need to make sure that you know your topological degrees of freedom. Otherwise, you may mess up. Okay? So you need to assign a non-zero number of degrees of freedom even to a topological sector of the theory. And in fact, if k is large enough, it may exceed the f of a scalar field, which is propagating. So a topological degree of freedom may carry more degrees of freedom than a propagating degree of freedom. Okay, so this is very surprising, but it's crucial for the consistency of the whole setup. Okay. So let me just show you an example of an RG flow, a non-trivial RG flow in 3 dimensions, which works. when you include these f's correctly. So a simple RG flow in 3 dimensions is that you have a U1K Chern-Simons theory. So this is topological by itself, but you add NF fermions. Okay, that's an interesting theory for condensed matter physicists. And you take the fermions to have charge 1. Okay. Now, this theory has an F which we can compute. So that would be our UV theory. And we will take K to be very large so that we can compute the F. This is an interacting field theory, so we don't know the exact answer for what is F. But when K is very large, then it's weakly coupled, and we can compute the 3-sphere partition function in perturbation theory. I'll take K so large that if the free field values saturate the answer, so the free field values are a good enough approximation. So FUV has a half log K from the topological sector, and then there is the contribution of NF fermions, and that's it. So we have NF times the F value of a fermion, which I did not quote, but I'll just tell you that it's log 2 over 4 plus Z of 3 over 8 pi squared. So 3Z of 3 over 8 pi squared. So this is F in the UV of this simple field theory. At large K, it's a weakly interacting field theory, and there are just small corrections to this F. Okay, now we can do the following thing. We can add the mass term to the fermions, and then we have an interesting RG flow. So we start from U1K plus NF fermions, but in the infrared, we've given a mass to all of the NF fermions. So that means that the infrared theory has no propagating degrees of freedom. It's a purely topological field theory because we've got rid of all the propagating fermions. And it turns out to be just a U1K plus minus NF, a topological field theory. Okay? So when it's known in 3 dimensions, it's a known fact that if you give a mass term to fermions, they shift the Chern-Simons level. This is just something that you would have to believe me if you don't already know. So we can now compute F infrared of this theory. And that's just a half log of K plus minus NF, depending on the sign. Okay? And you can now check at home that in the regime of validity of these computations, which is large K and finite NF, this can never exceed that. So the theorem is satisfied, non-trivially. This is just an example of how it's satisfied, but you can see what are the potential uses for such inequalities that in the many systems we don't know what's the infrared field theory. And you can rule out conjectures for the infrared field theory. For example, somebody would claim that the infrared theory has 100 scalars. You check if it's satisfied, and it may not be satisfied. And there are many examples of this sort. The previous conjectures for the infrared phase of some interesting interacting gauge theory were not correctly guessed. In this case, there is nothing to guess. We know the RG flow. It's a weakly interacting system, and we just see that it's satisfied. But in other cases which are strongly coupled, we can rule out guesses for the infrared phase using such inequalities. Okay, now let me mention the connection to entanglement entropy and also free QED. So free QED is an interesting subject. So how do we deal with free QED? Suppose the UV consisted of a free gauge field. What do we do with free QED? Okay, this is what I'll do in the last 10 minutes, and tomorrow we'll discuss the entanglement entropy of 3-dimensional field theories and 4-dimensional field. But now I want to concentrate on what should we do with free quantum electrodynamics. Supposing that in the UV there is a free electromagnetic gauge field, not a Chern-Simons term, but an actual F mu squared. So free QED. Well, the point is that the 3-sphere Lagrangian, so let's use the scalar language. So I'm going to use Poincare duality, and I'll try to describe the situation using the compact scalar. That's a better language, as we've seen. So the 3-sphere Lagrangian now has the kinetic term d phi squared, And previously, we also had some coupling to curvature, as you remember, r phi squared. But since our scalar now is compact, this is not allowed. This is not allowed. So the three-sphere Lagrangian for free QED in the scalar language needs to be dead. We cannot add a curvature coupling. So the path integral that we need to solve is d phi e to d phi squared, square root of g, d3x, with a minus. So we need to solve this path integral, and that would be, so the log of this path integral with a minus sign would be f of free QED. But this is clearly infinite. Because there is no curvature coupling, the integral over the zero mode of phi, just constant field values phi, gives an infinite answer. Okay? So this needs to be regulated somehow. If the scalar is, so it gives an infinite answer if the scalar is completely non-compact, but if the scalar has a compact radius, if it has a finite radius, then it gives a finite answer. Okay? So let me tell you what you get after some computation. So this is infinite. This is infinite if phi is non-compact. But as we've discussed, the scalar that is dual to a free gauge field in 3 dimensions is actually a compact scalar. And its radius of compactness is given by square root of f. So this is a scalar that is periodic. For this case, it's completely finite. So you can actually compute this partition function for the compact scalar. And what you get is log of FR. Of FA, sorry. FA is the radius of the sphere with a minus a half. You get minus a half log of FA. So this is what makes the scalar subtle. The S3 partition function depends on the radius, unlike all the other cases that we've discussed before. In 3 dimensions, there is no dependence on the radius for conformal field theories, because when you change the radius, it's just a conformal transformation and it doesn't affect the partition function because there are no anomalies. But for the free scalar field, the compact scalar field, which is dual to free QED, this argument is not possible because that theory is not conformal invariant, it's only scale invariant. And there is no scale current. So you can actually trace back this disease that the partition function depends on the radius to what I elaborated on in the beginning. That this is a theory for which there is no scale current, but it is scale invariant. So you could ask, are there any observable consequences to the fact that this theory is scale invariant but doesn't have a scale current? And the answer is yes. The 3-sphere partition function depends on the radius just because of that. So this is possible because there is no scale current. If there were a scale current, you could easily prove that it can't depend on the radius. Another interesting consequence of that is that, as we've discussed, the free QED, when free QED is in the ultraviolet, it corresponds to a scalar of 0 radius. So f going to 0. And then you see that the log goes to minus infinity, and because there is a minus out front, this goes to plus infinity. So that means that the number of degrees of freedom associated to a free QED is infinite. Okay, so in the ultraviolet, we know that f is going to 0 effectively. This is in parentheses. This is effectively. And therefore, f is going to infinity, the number of degrees of freedom. So the number of degrees of freedom associated, to a free gauge field is infinite. So that is somewhat unfortunate because many interesting renormalization group flows that are interesting to condensed matter physicists begin their life from free gauge field that flows to something. And therefore, the F-theorem does not place interesting constraints, because it just says that F infrared is smaller than infinity. But there are many tricks to overcome that. Some of them you can find in references in the notes. So people have found smart ways to overcome this, and there are interesting constraints that you can impose nevertheless. But this is strictly speaking correct. Now, this allows for an interesting reinterpretation of the log k for Chern-Simons theories. So the argument is as follows. Let's start from f squared, 1 over 2 e squared, and add the Chern-Simons term, a wedge dA. This describes a renormalization group flow from QED in 3 dimensions to U1k. So as you know, the Chern-Simons term in 3 dimensions gaps the theory. So it makes the infrared empty, just as topological degrees of freedom. But in the UV, we just have a free gauge field. This is irrelevant in the UV, and then this is irrelevant in the infrared. So this is relevant in the infrared, this is irrelevant in the infrared, and this is relevant in the UV, this is irrelevant in the UV. So we flow from this theory, which contains just that term, to the theory that contains just that term. Now, the partition function here is minus a half log fa, where a is the radius of the sphere. But because the theory in the infrared is gapped, you can imagine that you somehow stop the RG flow when the radius of the sphere is more or less the mass of the photon. And the mass of the photon is something like e squared k. So this is inverse. So therefore, if you just plug this radius of the sphere into this formula, you find that f of the infrared is exactly a half log k that we discussed before, plus corrections that are independent of independent of k and so on. So you see that there is an interesting reinterpretation of this a half log k from QED3. And you can also see why QED3 has to have infinitely many degrees of freedom. This theory can flow to a Chern-Simons theory with any k. And since f of Chern-Simons theory is a half log k, the only f that you can assign to create QED3 is infinite. Otherwise, the inequality would not be satisfied. And also, you can understand that this a half log k is really just a consequence of the radius-dependent 3-sphere partition function for this free QED3, because the radius is just set by the mass of the kk of the gauge field, and that explains all. This ties together all these facts that we discussed. So in summary, just in the last half a minute, free QED is a subtle theory which is scale invariant but not conformal, but it's even worse because there is no scale current. That explains why its free sphere energy is infinite. So the free energy on the 3 sphere is infinite. That's consistent with the F-theorem because we can flow to these Chern-Simons theories with arbitrarily large k, and they have some large f, and it's consistent with the F-theorem, and the F-theorem holds essentially is supposed to hold in every 3-dimensional renormalization group flow, and it imposes very stringent constraints on the possibilities of what can flow to what and what are the possible dynamics of various 3-dimensional theories. So this is the idea, and next we'll discuss the entanglement entropy in 3 dimensions, which you can guess also knows about F. That's something that I will explain. And then we'll switch to 4 dimensions. Okay, are there any questions?